In the programming assignment related to this lecture on the AllDifferent constraint, you will have to implement in MiniCP the domain consistent filtering algorithm that we just have seen. So I would like to take a few minutes to give you a little bit of clues on how to implement and succeed in this programming assignment. First, I would like to discuss something about the state restoration of the AllDifferent constraint and the incrementality aspect. What is important to notice is that when you go down in the search tree and you are removing values from the domain of the variables, assume that, for instance, you have computed a maximum matching there in this node for an AllDifferent constraint of your model. Then, as a consequence of this and the fixed point algorithm and the subsequent removal of some other values, it's possible that some of the edges that were matched in the maximum matching do not exist anymore in the variable value graph. But still, some of them might still be valid ones. And so what you can do is, when you go down the search tree, you can simply keep the ones that are still valid and start from there and warm start the augmenting path algorithm and try to discover a new maximum matching for the feasibility check. Okay, so once you have updated the graph and found a new maximum matching, when you will backtrack, it's very important that when you backtrack at an ancestor node, you can only recover edges. As a consequence, the valid M prime that would be there when you backtrack might not be the same one as you had previously computed in this node when you will backtrack, but it's still a valid one and you can continue from there. So it means that there is no need to store the maximum matching in a reversible state, right? Since when you backtrack it's still valid, you can only add values to the domain and recompute and restart the augmenting path algorithm from that point. That's one important aspect about incrementality of computing the maximum matching. For the programming assignments, we provide to you a very important building block. That's the class maximum matching. That's the skeleton of the class. So in the skeleton of the class, the constructor asks you the n variables of the AllDifferent constraint. And once you call compute there, you give it as arguments a variable here. It's as an argument you give n variables. Okay, here you also have n variables. It will give you for each variable the specific value that is computed for the maximum matching, right? And there is also a method to check if the maximum matching was of cardinality n or not. So that's one thing that we provide to you to implement the AllDifferent constraint. At least you don't have to bother with the computation of the maximum matching. You just have to assemble the very important building blocks to make sure that you understand how it works. And the other important part that we provide that is already implemented for you is the computation of the strongly connected components. Okay, so we have a method there that computes a strongly connected component for the graph. Okay, that's a graph with let's say m nodes. Okay, and so it returns here an array of size m, and this array of size m will give you the identifier of all the strongly connected components that the corresponding node of the graph belongs to. Okay, so of course you need to have appropriately chosen the identifier for the graph. So what we propose to you is that you use this labeling for the nodes to choose the identifiers. So what we have used here is, you see, that's the value from 0 up to n-1 for the variables. Okay, there. And then we continue like that for the values. Okay, we continue. So there were here 9 variables. So the largest identifier for the variables was 8. So the first value will get the value 9, 10, and so on. And we assume that there is no gap here in the range of values. Okay, we started from the minimum value of any domains in the scope of the AllDifferent constraint, and that's the maximum value of all of them, right? So we continue like that so that we have a dense utilization of all the identifier. And for the dummy nodes here, we just take the largest identifier for the value nodes, +1, and that will correspond to the dummy node. Okay? And the graph API is an interface that you can implement. So here I will simply pre-compute my incidence adjacency list of the graph, right? And if you ask me what are the incoming nodes to this node, I return immediately the array here. It's an iterable, okay, it's an iterable, so it means, for instance, a list. And that's the list of all the nodes that are incoming incident into that specific node IDX. And that's the nodes that are adjacent but outgoing from that node IDX. Okay, so in the AllDifferent implementation there, you need what I have implemented, and what we provide you in the skeleton is here you need to implement the graph, right? You need to implement the graph, and this graph will return the adjacency list, corresponding adjacency list for all the methods. So what needs to be performed is you need to do the update to update the adjacency lists that are represented here, right? I told you it was a list. It's an array of array lists for the incoming nodes and for the outgoing nodes of every of the nodes. Okay. So you will see that there is a to-do in the propagate method. So in the to-do, the first thing that you need to do is first compute the maximum matching. You need to update the range of values. You need to update the graph, okay, so that the adjacency list there is correctly computed, okay? And then you can use the strongly connected component based on that graph to make sure that you remove safely the edges that do not belong to some maximum matching, as we have seen in the previous video. The overall time complexity of the AllDifferent constraint is m multiplied by the square root of n, where m is the number of edges and n is the number of variables. Okay, and so the number of edges is the number of values that you have in each of the domains. A funny fact is that the bottleneck of the computation in practice is not as you could have expected the computation of the maximum matching due to the Hopcroft-Karp algorithm, but instead it's the computation of the strongly connected component that has a time complexity that is better than the one of the maximum matching. Okay, and why it's the case? It's because when you compute the strongly connected components, you do it from scratch. And it's not the case for the maximum matching. For the maximum matching, you are very incremental, and therefore you rarely will pay this time complexity. In practice, that's an upper bound, but in practice, the real time complexity will be lower than that one, and the real bottleneck of the computation is more the computation of the strongly connected components in the transform graph.